Hello everyone. So today I'm here to discuss about Gantry Girders. So it is a topic of design of steel structures. So before starting, I would like to tell you what you mean by Gantry Girders. Okay. So you might have a thought in your mind. What are the Gantry Girders made up of? Okay. So Gantry Girders is nothing but it's a beam which is made up of a steel material. Okay. So it is a beam where the span is laterally unsupported. Now, what do you mean by laterally unsupported beams? So before that, let me tell you what do you mean by laterally supported beams. Okay. So when the compression flange is supported using lateral supports to avoid buckling, then this type of beams are known as laterally supported beams. Okay. Now, when a beam is bending, then there is a tendency for the top flange, which is in compression, to pull the section out of the plane, and hence it will cause buckling. So in order to prevent this, it is important to restrain the compression flange by providing supports such beams are designated as restrained or laterally supported beams. Okay. So the reverse is the case for laterally unsupported beams. So what are this? When such lateral supports are not provided, obviously, to the compression flanges, then there will be chances of buckling or something. Then they are known as laterally unsupported beams. Okay, so we have seen that as it is laterally unsupported, so the bending stress due to compression has to be calculated. Okay, so now it is not symmetrical. The beam is not symmetrical. So we have to find out the bending stress due to compression using the IS code. So here for steel, we generally use IS 800 1984. So here also for the gantry girders, we will use this IS code. So next, what are the uses of gantry girders? The most important use is gantry girders are basically used for carrying the moving loads. Okay, so we have to find the position at which the maximum bending moment and maximum shear force will occur. Okay, why? Because as the trolley will move, then some impact load will also come in addition to the actual load. So what we have to do? We have to add the impact load with the actual load to get the total load. Okay. Next, we'll come to the components of crane system. So basically we can see there are four components of crane system. The first one is the cross girder or the crane bridge. Now the cross girder or the crane bridge is the major structure in the crane system. Okay. So next we have gantry girder. We will study that in detail. And then we have crane runway or rail. Then we have trolley or crass. So the trolley is the one through which the load is passed. Okay. Now it is mounted on the crane bridge. We have a small diagram that is of the top view of a crane system. Okay. So we can see here the crane girder. See, this is the crane this is the gantry girder. Okay. This is the gantry girder which is placed between the columns or stanchions. These are the two columns. Okay. Now here you can see the crane bridge. This is the crane bridge. This is the trolley. Now the crane bridge through which the this is the crane bridge through which the trolley will move to and fro. Okay. So next we have the components of crane system. Now as you can see the diagram, the gantry girder is placed on the this is the gantry girder. You can see this is placed on the column or stanchion. Okay, this is the column or stanchion. Now the column or stanchion is connected with the bracket. Okay, Now on the top of the bracket, we can see a packing is provided. On the top of the packing, the gantry girder is provided. So the crane, and then there is a rail placed on it which is connected to the crane bridge. Now you can see that the crane is kept on the gantry girder. Okay, and on the crane bridge you can see a trolley or crab which is moving, as I already said in the previous diagram. So the load is kept on the hook is connected to the trolley or crab. Okay, now on this hook the load will be attached. So what will happen when the crane, when the trolley is going to move to carry the moving load, then the bending moment will come into picture. So we have to find the maximum bending moment and maximum shear force or reaction at the gantry girder so that we can design it accordingly. Okay. So basically what we see that the gantry girders are examples of laterally unsupported beams in industrial buildings. Okay. So these are provided in almost all the industrial buildings. Okay. Forward, for what? For lifting and the transportation of heavy loads. Then the gantry girder is subjected to rolling loads also in the form of two concentrated wheels which is spaced at a fixed distance. B, small b. We will denote it as the distance between the wheels. Okay. Now coming to the profiles used for gantry girders. These are some of the profiles that are used in gantry girders. The first profile, I girder. Second profile, I plus channel girder. Third profile, I plus angle girder. Fourth, plate girder. Fifth, channel plus wave and flange plates. And the last one is the gantry truss using I cords. So these are the different arrangements. Like the first one we can see only I girder is provided. In the second one, I section is provided with the channel section. Okay. Next, the I section is provided with angle sections. So in this way, there are combinations of sections. Okay. So generally we use the first three in our gantry girders mostly. So this is all I have given. Okay. Now we will move to the design criteria. So we will start with the design. So before that, we have to know about the design criteria. Okay, the first criteria. The gantry girders are laterally unsupported at the columns. Okay, to be very clear. The deflection of the gantry girders under dead load and live load, it should not exceed the values which is given as per the clause. I have mentioned the clause also. Clause number 1.13.1.3 of IS 800 1984. Okay. Now, due to lateral thrust, what will happen? The gantry girder will subject to asymmetrical bending. Okay. So, the gantry girders are subjected to impact and longitudinal loads. So, due to the movement and stoppage of the crane. Now, the additional values of these loads will be taken as per IS 875 and which is given by this table. So we'll find from this table. Okay. So in the left column, we can see the type of load will be given. In the right column, we have the additional loads for those. Okay. So first, we have vertical loads for two types of cranes. One is electric operated cranes and another is hand operated cranes. Now I'll tell you one thing, that hand operated cranes are not in use nowadays. Okay, we only use electric operated cranes. Okay, so for EOT, electric operated cranes, or EOT, we use 25% of the maximum static load. Okay, for hand operated cranes, we use 10% of the maximum static load. Similarly, for horizontal forces transverse to the rails, for electric operated cranes and for hand operated cranes also, we use the additional load of 10% of the weight of crab and the weight lifted by the crane. Next, the horizontal forces along the rail. It should be 5% of the static will load. Okay. This is the maximum permissible deflection. You have to check if the actual deflection is exceeding the maximum permissible deflection or not, as per the IS code. Now, this is given in the IS code as per clause 1.13.1.3. Okay. So, if it is exceeding the values, then we have to redesign it. Okay. So where we can see that where manually operated cranes are operated, and for similar loads we have L by 500. So similarly, when for electric operated overhead traveling cranes operate up to 50 tons, we have L by 750. Okay. The third one, where electric operated overhead traveling cranes operate more than 50 tons, then we have L by 1000. Okay. So other moving loads such as charging cars, etc., we have L by 1000. So where L, what is L? L is the span of crane runway girder. Okay. Now we'll come to the permissible stress. Okay. So in the permissible stress, the allowable bending stress for bending in horizontal plane is taken equal to sigma BC. Sigma suffix BC. So sigma suffix BC for horizontal equal to sigma BT, that is equal to 0.66 Fy. So the next, the allowable bending compressive stress, that is sigma BC for vertical, sigma BCV, okay, for bending in vertical plane is determined on the basis of critical stress, that is FCV. Okay. Now, according to clause 3.9.3, addition of the stresses in both the planes need 10% increase for the design. Okay. Now, again, according to clause 3.9.4, no increase in main load will be required. Okay. Uh, for main load is the main load acting on the structure. So, what do you mean by this? So, it is said that according to clause number 3.9.3 of IS 800 1984, the allowable stress in axial tension, axial compression, bending stress, and allowable stress in rivets may be increased by 10% for the design of gantry girders. Okay. For the combination of both, we will have to add both sigma BC for horizontal and the vertical. Okay. And then we have to increase it by 10% and check. And the last one, it is said that according to clause 3.9.4, where the wing load is the main load acting on the structure, no increase in the permissible stresses will be allowed. Okay. So now, okay. So now we'll start the design procedure. So we have in total 12 steps. Okay. So we will start from the first step. Here is step number 1. In step number 1, we can see that the maximum vertical load, for the calculation of maximum vertical load, we have to we have to know the three notations, that is WT, WC and WD. Okay, so the total vertical load will consist of these three. So what is WT? WT is the weight of the trolley or crab, and WC is weight of crane girders, and WD is self weight of girders and rails. Okay. So, and the load to the gantry girder will be maximum when the trolley wheels are closest to the girder. Understand? So here W1 will be given by WT into B minus A by 2B. So here capital B is nothing but the distance between the gantry girders. Small a is the distance between CG of girder and trolley. This is small a, and then we can see that W1, what is W1? Here W1 is the load transferred to gantry from each wheel. W2 is load transfer to girder due to crane. Now as you're having 4 wheels are there, each at one end, so W2 will be what? The weight of crane girders divided by 4. So it is WC by 4. Now the total load will be given by W equal to W1 plus W2. Earlier we have already we have already got W1. Okay, W1 is WT into capital B minus A by 2B plus this WC by 4. Okay, so we can see that when the impact allowance will be considered here in this case, so we have to increase the maximum load by 25% to account for the impact. So along with this W, we have to add the 25% impact load to get the total load. Okay, now moving to the step 2. In the step 2, you can see that we have to calculate the maximum bending moment, okay, due to vertical loads and the maximum shear force also. So first we have to calculate maximum bending moment. So you can, we'll first calculate, we'll see the position of maximum shear force first. Okay, so in the first diagram, we'll see that there are two loads which are at a distance of B. The spacing between the two wheel loads are B. Okay, from this is the position when we'll get the maximum shear force. Now in the next diagram, we can see a span which is having a length L. Okay, now this is L by 2, this L by 2 and this is L by 2. Okay, now we can see that if the wheels are spaced at distance B, as I said that the distance between the two wheel loads will be how much? B. So the distance between two wheel loads will be B. So this is this will be how much? B by 2, of course, and this is B by 2, the other half. Now, if the wheels are spaced at B distance and the distance between the CG, okay, of the wheel load, this is the CG of wheel load, okay, to the one load, this is the CG, okay, this is the CG, and to the one load should be how much? B by 4. So we will get here maximum bending moment. So this is how the position of wheel loads should be placed in the span in such a way so that we get the maximum bending moment. Okay, now we have to calculate M1. For this we are having two criteria. One is B is lesser than 0.586 L and another criteria is B is greater than 0.586 L. Now for the first criteria, if B is lesser than 0.586 L, now here L is the span of the, L is the length of the span. Okay, so we will have to calculate this one, and then if we see that it is it is greater than B, then we have to place one of the wheel at B by 4 from the center of the gantry girder. Okay, and if B is greater than 0.586 L, then we have to place one of the wheel at the maximum span, okay, to get the maximum moment. So these are the two criteria. Then we have to assume self weight. Okay, so what will be the self weight? It will be 2 into total load, that is W is total load, divided by 250. This will give you the self weight, and the unit will be kilonewton per meters. Okay, then W2 is nothing but the weight of rail. Okay, I have not written here, but you can just keep in mind that you can note it down also. W2 will be 0.3 kilonewton per meter. W2 is weight of rail. Now the total UDL on the girder. Thus the total UDL on the girder will be heading this two, W1 plus W2. Okay. Total bending moment. Total bending moment will be M1 plus M2. Now what is M1? It will be the position of maximum bending moment. M2 is WL square by 8. Okay. Now next step, that is step 3. Okay, I didn't mention step 3 here. Okay, this is the step 3. In step 3, we will see that we have to choose a suitable section. Okay, so now for choosing the suitable section, we have to take sigma bt equal to 0.66 fy and z equal to mx by sigma bt. Okay, so this is the formula. This is nothing but z is section modulus. So this is mx that we have already calculated bending maximum bending moment and uh, divided by sigma bt. Okay, so now we have to select an I section. So we will choose a section which is a combination of I section and general section. Okay, so I section or any other section also you can choose, and we have to add 10 to 20% with the actual value of z. Okay, now we will choose another section, that is a channel section, which is having a depth of 50 mm more than the width of the flange of I section. So what do you mean by this? See, this is the I section, okay, and this is the channel section. Now suppose this I section is having width of 250 mm. Say, okay, let us take an I section which is having you will get uh, the dimensions from the steel code book. Okay, as per like what specifications of this sections you are taking, based on this you will get the dimensions. Okay, suppose we have chosen an I section which is having width of 250 mm. Now what you have to do, the depth of channel section should be more than 250. That is, it should be at least 50 mm more than 250. You have to take at least 300. Maximum you can take more than that also. Okay. So the width of the I section, the depth of the channel section should be more than 50 mm from the width of I section. Okay, width of the flange of I section. This is the width of the flange. Now, coming to step 4, we have to calculate the neutral axis and the value of Ix. Now, we have to find the neutral axis depth of the combined section. Okay. Next step, we have to check for the bending tensile stress. Now, bending tensile stress is denoted by sigma bt. Here, we have already taken sigma bt, it is equal to 0.66 fy. Earlier in step 3 we have taken. Okay, so sigma bt calculated, the sigma bt which we will calculate should be lesser than the sigma bt. Okay, so if it is exceeding, then we have to redesign it. Okay, now moving on to the step 6, we have to check for bending compressive stress, that is sigma bc. Now we will get sigma bc from FCB and Fy. So FCB is nothing but critical bending stress, and FCB is given, sigma bc is given by m by I into Yc. This is the bending equation. Okay, from the bending equation we get sigma equal to m by I into Y. So again same thing, we have to see whether sigma BC calculated should be lesser than sigma BC or not. Okay, it should not exceed the value of sigma BC. A calculated value should always be lesser than the sigma BC value. Okay. Next, coming to step 7, we have to calculate the bending moment due to horizontal load. Okay. So in this, the calculation of transverse horizontal loading equal to, we will get by WH equal to FH by 2. Okay. So here My equal to Mx1 plus WH divided by W. So here we can see that the bending moment will be resisted by compression flange. Understand? So you can see this, the bending moment will be resisted here by a compression flange. So we have to calculate My like this. Next, moving on to the step 8. For this, we have to calculate the compressive stress due to horizontal loading. Now we have to find two things. One is we have to calculate the moment of inertia of the compression flange, and we have to calculate the compressive stress due to horizontal bending. Okay, this. Now, for finding the moment of inertia of the compression flange, what we have to do, we have to uh, find this Iy of compression flange. This is nothing but Ixx of channel section plus half of Iyy of I section. Okay. So you can see that we can find the Iy of compression flange. Next, we have to calculate compressive stress due to horizontal bending by using this formula. Sigma BC calculated already, we have calculated in the previous step. In step 6 we have already calculated. So this equal to Mx by Iy into Iy of Cf, this value into X. Okay, what is X? X is the maximum fiber distance, that is Hc by 2. Now you can ask me what is Hc. So I'll show you. Suppose this channel section. Okay. What is the height of the channel section? H. Small h. Now up till this part will be how much? Hc by 2. Okay. This is total is Hc, height of channel section, and this is Hc by 2. Okay. So this is maximum fiber distance. X equal to Hc by 2. So this is maximum fiber distance. Now step 9. In step 9, we have to check for maximum bending stress. Now, this is nothing but the addition of both. That is sigma BC calculated for vertical and sigma BC calculated for horizontal load. Both. Okay. Now, the combination of both this should be lesser than 1.1 sigma BC. Now, we have already calculated sigma BC in step 6. Okay. Now, if we don't get the value of the, that is the total addition of this sigma BC lesser than 1.1 sigma BC, then we have to redesign the steps starting from your say step, we have to do it from step 3 onwards. Okay. Now step 10, you have to do, what is a step 10? Calculation of stress due to longitudinal force. Now, the longitudinal force along the rail, that is given by FLH, F suffix LH, equal to 50% of the total wheel load. We have already got these values, right? So this is equal to 2 into total load, W. Now MLH, it is nothing but horizontal longitudinal moment, M suffix LH. It is given by FLH into HR plus YC. Okay. Now, what will be the stress in horizontal direction? FLH by 2 plus MLH by 2. Now, the stress in the horizontal direction will be very small. Okay, as these two are very small. FLH is very small value, MLH also very small value. So addition of both these two, okay, this should be divided by 2 and this divided by 2, we will get the total value which is also very small. Okay, so on step 11, we will have to check for the shear stress, which is one of the very important steps. Now to calculate the shear force V1 due to wheel load and add 25% as impact factor. We already studied about impact factor earlier. In the table, I have already mentioned what impact factor you have to take. Okay, so we have to add the impact factor now. In the second point, it is said that the shear force V2 due to dead load. We have to also calculate the shear force due to dead load. Now we have to add both the shear forces. That is capital V equal to V1 plus V2. This is actually your suffix. Okay, V1 will be in your suffix and V2 also in your suffix. Now we can check it how VA calculated equal to V by small h into TW, which is smaller than 0.4 Fy. So what is this? This is shear force developed. Okay, it is according to the IS code. So if it is exceeding the value, this shear stress developed, if it is exceeding the value of 0.4 Fy, then we have to redesign the step again. That's what I said you in the earlier step. Okay, we have to redesign from the first beginning. We have to redesign. So here we have to check it. Okay, now coming to the last step, that is the design of riveted joint. Now we have to place the rivets in such a way, so we have to calculate the intensity of shear stress per unit length. Now for this step, I'll tell you the design of riveted joint. You can do this step also, or else you can do it in other way. But I have done it in this way. So the calculation of the intensity of shear stress per unit length, that is small q. Okay, it is the intensity of shear stress. It is given by capital V into AFC into Y1 divided by IX. Okay. Here, what is AFC? Is the area of cross section of the flange of the channel. Now keep in mind, this is the area of the only flange of the channel section. Understand? AFC. Y1 is distance of the CG of the flange of the channel from the neutral axis. I think I have already said in the earlier diagrams and earlier steps. Just have a look. And Ix is moment of inertia of the combined section. So we have to calculate all these steps and we have to do one by one all the steps, and we have to do the design for gantry girders in this manner. Okay, so next in my next video I will try to solve a problem in this following steps. Till then, please have a look, and if you have any suggestions you can write in the comment section below. Okay, thank you.